Hey, what's up, guys? This is Chung. So, today, number 127, word ladder. So, you're given like two words, at the begin word and end word, and a dictionary word list. And you need to return the shortest transformation sequence from the begin word to the end word. And you're only allowed to change one letter at a time. And each transformed word must exist in the word list. And return 0 if there's no such transformation sequence. So there are like two examples, right? So the first one is we're trying to transform from heat to cog, and the output is 5 because we can do this transformation. And the second one is the 0 because there's no way we can transform from heat to cog. Okay, and there are some constraints here. So the begin and end word, the length limit is with it's a 100 letters, and the word list is like it's up to 5,000 words. Okay, and all the words they only consist of lower English letters. Okay, and all the strings in the word list are unique. So that's the all the constraints here. So for this problem, since we're trying to get the shortest transformation sequence, so this one is like a classic problem to use the BFS, the breadth first search, to get the shortest path from the starting point to the ending point, right? And the concept is pretty straightforward. And the tricky part is that, we need to somehow find like the the edges, right? Basically from one word, what are the valid edges from the current word to the next word? So the condition is that, so the edges, right? The neighbors has to be like exist in this word list. Second, it has to only has one difference, right? As the current word. And the question is that how can we calculate that? I mean, there are like uh different ways you can do it. I mean, one of the ways is that, we can try to pre-calculate the we try to pre-calculate each word's neighbors, right, from the word list by looping through the each of the word here, and then we try to compare with all the other words, right? And if their difference is one, if it's one, then we just add that word to the edges, right, to the of the current one. So and what's the time complexity for that, right? So since we're going to loop through each of the word, right? So we have a 5,000, right? That's going to be the 5,000 times, and for each of the word, we're going to compare with all the other words. So that's going to be another 5,000, right? And to compare the difference, right, we also need to do another like loop, right, to compare the letters one by one. That's going to be a 100. Right? So that this is going to be the total time complexity of of doing that. This one, I think this will work because the 5,000 times 5,000 times 100, yeah, I think it will pass. So this is the first like way of doing that. And then we're gonna store like the dictionary, right, where the key is each of the word, and the value is a list that's the of the neighbors, right? This word can transform to. And how about the second one? So the second one is that, since every time when you guys see like the consist of lower letters of English letters, so you should always like be aware that that means that at each of the the position there can only be up to 26 different letters, right? Because that's the English letters. So another way of doing this is that, so first we convert this word list into a word set. Okay. So this is gonna be a O of n time, right? So after converting to the list to a set, then when we check if a word exists in this set, it only takes one time. And after that, right? And every time when we have like a word here, right? When we have a word, we can just loop through each of the position of the word, and then we're gonna try to replace I mean the current position with all the letters from A to Z, and then we will have like a new word, right? And then we just need to check if the word exists in this word set. So what's the time complexity for this approach, right? So for each of the word, right? For each of the word uh we have like 100, right? So we have 100, and then on each of the position, we're gonna try 26 letters, right? That's gonna be a 26, and and then after that, I guess we're gonna try to, hmm, yeah, I think that's pretty much it is, right? So even though after this one, we're gonna concatenate that to back to the new word, that's gonna be another like 100, right? To concatenate everything together. But in total, so this one's going to be, as you guys can see, this one is just much faster than the first approach, right? So, and that's what we're going to use here in this case. Basically, we just every time when we have like a word, we just try to place each of the letters with 26 English letters, and then we just go from there. Cool. So then let's start coding here. So first, let's try to convert this word to a set, right? Okay, and then the next one is to do the BFS, right? We need to have like the queue, right? The DQ, and the DQ will start with the beginning word. Okay, and then scene set, right? That's the scene dot add beginning word. Okay, and then we have an answer, right? Answer equals to 1. So because here, so we're making like 4 like moves, but we are returning 5. That's why I start from 1 here. And uh, next is just like the DFS template, right? So for this thing in range of length of the queue, right? So we have a current. So the current is the equals to queue dot pop left, right? And if the current is the same as the end word, right? So this is the exit conditions, which simply return the answer, right? Else in the here, which increase the answer by 1, right? And then if there's no match, right, after consuming everything in the queue here, we just return 0. So here, and we just need to look through each of the character, right, in the enumerate of the current. And we're gonna have like a new word. So the new word is what? It's the by concatenate, right? Concatenating so the left parts, right? So the left part is it's everything that's before I, and then so the current one is the one gonna be the ones we're gonna replace, right? So we're gonna use the chrord, right? Dot a plus, sorry, So I forgot to have another loop, right? So for j in the range of 26, so which means that we're gonna loop through 26 letters. So here we have like that's the Python way to convert the to loop through from A to Z, or you can just enumerate list all the letters from A to Z, and then you can just loop through it. So here I'm just using the ORD and CHR function to help me do that. And then the remaining part is just the current uh, starting from I plus one. So this is going to be the new word, and we just need to check if the new word is in the word set, right? And the new word not in scene. If that's the case, we can just continue our BFS search, right? New word, and also the scene added to the scene set, right? Okay. Yep. I think that's it. So let's run the code. Accepted. Submit. Yeah. So yeah. So it's accepted. So the total time complexity for this, it's the what? The let's see. Yeah, so the total time complexity for this is first so the worst case scenario, we'll loop through all the word in this list, right? So it's gonna be 5,000, right? And then for each of the word here, right? For each of the word, we're gonna first we're gonna have like the for loop here. So that's gonna be 100, and 100 times 26 times 26, and then 20 inside the 26 we have this one. Um, Here I believe it's another 100, I'm assuming, because to slice the words and concatenate them together, I think it's another 100. It's a linear. That's why that's the total time complexity for this problem. Mm, yep. I think other than that, it's just like a classic BFS problem. So uh, the only part you need to be uh, think about it a little bit more is that how can you find from the current word, how can you find the neighbors, right, for the current word? So, and the way we're using it, the way we're doing it is by looping through each of the letters and try to replace the letters with all 25 lower English lowercase letters. And yeah, there you go. Cool. I think I'll just stop here. And thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.